Many of you are involved in designing sensors and other edge devices for the Internet of Things. Years ago, sensors and data gathering were separate, connected by wires. Whether in a car, plane, or buried underground, these devices measured what they needed to and reported back. The base station would collect that data, recording it on a wire or paper for later collection. Now we're in an era when device design must gather multiple sets of data, most of which needs to be time-sensitive and power fail-safe. Base stations and sensors are often in the same unit, and a microprocessor adds capability and control. Today we're going to talk about upgrading that design to use an RTOS and a file system package, resulting in a better collection and communication of the data and the added possibility of certification. Once microprocessors moved into edge device designs, a lot more control was available to the system architect. In addition to a microprocessor upgrade, devices also added real storage, from EEPROM to micro hard drives to fully programmable flash media. Data could be stored by simply logging to the next block location. Avoiding a full disk means using a looping log storage, which is essentially how this seismogram from the Weston Observatory works. Finally, a simple file system could be incorporated. Most available RTOS today provide an old desktop file system called FAT for this purpose, though FAT wasn't designed for this environment. Let's dive deeper into these topics with Matt.
Thanks, Tom. So Tom's given us a little introduction there to some of the increasing complexity that we see in embedded systems and how that's impacted storage devices, data storage. Now we're going to consider how developers structure their code in order to deal with this complexity. So we'll begin by looking at really the simplest approach to embedded systems design. This approach is still used in a wide variety of embedded systems. This would just be a bare metal system, or in other words, a foreground background system. So the foreground background name here relates to the basic structure. On the left-hand side of the screen, we see the background, which for this type of system would be our declaration of main, which is going to contain an infinite loop. The infinite loop is going to make a series of function calls, and that's really going to comprise the bulk of this sort of system. These calls would execute the fixed sequence. There's not really any priority or importance here. We just have this continuous series of function calls being made. The only exception to that sort of operation is when we get an interrupt. And so on the right-hand side of the screen, we see the foreground. These are going to be the interrupt handlers that jump into the foreground. They become the most important thing and execute immediately when we have any sort of urgent hardware event. So, very simple structure here. Most of us have written this sort of system and served developers well in a variety of projects. But there are drawbacks to foreground background systems, and one of the biggest drawbacks is that this approach really lacks flexibility. So when we're writing a foreground background system, we really just have two options as to where we can place our code. One option is we place code in the background loop. So that means we write a function call, we put it in that loop, and it's going to be executed as part of this fixed sequence of calls. That's fine for things that happen periodically. They don't have very tight deadlines, but it can be problematic when we have code with a deadline. We have a code that needs to execute in some sort of fixed response time. And so in those cases, we need to look at the foreground. Those are interrupt handlers. And for a simple system, this division here where we have two places to write our code is fine. We add our less important code in the background loop, and we add the urgent codes at the foreground. But this can become a problematic arrangement if we have a very complex system. We start to get a large number of ISRs or interrupt handlers. With the ISRs, we're typically going to be disabling at least a portion of our other interrupts. The ISRs are usually going to be somewhat difficult to manage and debug. It's not a very easy to expand model. And also, the prioritization that we have with our ISRs, prioritization and our nesting schemes are often not going to be portable. So there's some drawbacks here, and often to find an alternative to this system, developers turn to a kernel. So we see a kernel-based version of our earlier foreground-background system here. This is really just pseudocode. You know, it could be, we could use one of MICREM's kernels, MicroC-OS2 or MicroC-OS3. We could use another kernel. The concept is really the same in all those cases. We see on the left-hand side of the screen here is a couple of tasks. So we have an A to D task and a file system task in this case. These are just going to be C functions. But the big difference here with the foreground-background system is that rather than being executed as part of this loop where they're in a fixed sequence, the tasks in this case are going to be scheduled by the kernel. So the kernel is going to manage these tasks and will make scheduling decisions for the tasks based on the importances or priorities that are assigned to those tasks by application developers, as well as the current state of our system. So we'll look and see what other tasks are ready to run, and that's how it makes its scheduling decisions. We do still have ISRs in the kernel-based system. We see one of those on the right-hand side of the screen here. Big difference with the ISRs here is that we're going to have kernel services that allow those to interact with our tasks. So we can enable tasks to run from an ISR, provide some data, maybe a message to a task through an ISR. So ultimately with this system of tasks and ISRs that are prioritized and communicating or interacting in some way gives us is a portable and easy to maintain application framework where scheduling decisions are made as code runs. Now we can expand this concept to multi-core architectures. This is another area where you see some increasing complexity in the embedded system space. Now you have even Cortex-M based processors of that class that are being made in multi-core varieties. And so this is somewhat confusing sometimes, somewhat problematic for application developers. And so a kernel here can be a solution as well. With multi-core systems, we really have a couple approaches that we can take when we're talking about real-time kernels. One is asymmetric multiprocessing, or AMP. This is where we would have a separate copy of the kernel running on each core. We could have real-time kernels like MICREM software running on each core, or we could have a Linux on each core. We could have Linux on one core, real-time kernel on another. So we're fairly flexible there. The other approach we have in a multi-core system will be symmetric multiprocessing, SMP. This is where we have a single kernel or operating system managing all of the cores and assigning tasks to those different cores. So each of these approaches has its pros and cons, but overall a kernel or operating system in this multi-core setup is going to be very similar to what we see in the single core setup. It's going to be a means of mitigating the complexity of this sort of system.
So the CPU and RTOS have become more powerful, and the amount of data is increasing. The simple logging techniques that work with a small file are insufficient to handle multiple files with multiple simultaneous access. This arrow here represents both the volume and complexity increasing, both in embedded designs and in the world around us. A scalable file system is the best solution. And the best choice is one that can take you from a single file to multiple files to fully named folders and files up to a full POSIX implementation. Let's examine these and other requirements. If the software you have doesn't scale, it will have to be replaced. Adding new data source to a design should be an opportunity, not a challenge. In addition to being scalable, the ideal embedded file system should also be power fail-safe so that your gathered data is not lost. With the maximum erase count of flash media always decreasing, it's also important that the file system enhance the device lifetime. This is done by reducing an effect that we call write amplification. I mentioned the default file system solution of FAT earlier. For a small device, this file system has a lot of extraneous features such as subfolders and volume labels. This functionality can take up a lot of space in memory. As a rule, FAT wasn't designed for customization either, so removing these features is problematic. No validation tests are provided, so the application developer will have the added burden of proving any changes they make. Finally, the largest drawback, the FAT file system isn't designed to handle power failure at all. Our alternative is a transactional file system. The use of transaction points can prevent loss from power interruption. All of the media writes occur only to the working state of the media, leaving a known good state unaltered. A transaction point commits the working data to become the new known good state. This also allows a rapid and consistent mount time. No disk check or journal replay is needed. The boot algorithms merely need to figure out which disk state is the known good. With the proper transaction point settings, this method is also fully atomic, meaning changes are either fully committed or not done at all. No partial writes, no program logic needed to check for the situation. Let's look at one solution that meets the requirements we spoke about in the previous slides. Reliance Edge is designed for customization, providing everything from a full POSIX environment down to a set of file system essentials. In the latter case, a fixed number of files are essentially numbered inodes, and functions are provided to read, write, and set the size of these files. This allows a considerable savings in memory footprint without sacrificing any of the reliability in solid design. Reliance Edge was written to conform to the MISRA C 2012 standard and integrates well with Micrium's MicroCOS environment. Together, these products provide a well-tested and supported solution that is flexible enough to meet a wide range of needs.
So we've now got an introduction to some of the basic concepts behind Micrium's MicroCOS 2 and MicroCOS 3 kernels, as well as Datalight's Reliance Edge file system. In the next couple of slides, we're going to consider some of the details of using Micrium's kernels alongside Datalight's file system. So here we see a block diagram illustrating the integration of Micrium's MicroCOS 3 in this case. It also applies to our MicroCOS 2 kernel. But here we're showing MicroCOS 3 being used alongside Reliance Edge. The basic idea here is that when we use a software module like a file system and a multitask system with a kernel, there's going to be some kernel functionality that the file system requires. Usually the file system is going to need to lock shared resources, for example. It might need to signal tasks. So there's some code that needs to be written to allow the file system to utilize the kernel services. And that's work that's been done by Datalight and Micrium. So we've implemented a system like what you see in the block diagram here, where application code can invoke the file system services. File system will utilize the kernel. And of course, below that, you're going to have the low-level code and the driver code that's also shown here in the diagram. Ultimately, for application developers, the result of this integration is that you have a robust software platform where you can take advantage of scheduling and data storage capabilities in a multitask system. The details of the integration, the technical details, are really beyond the scope of this webinar. But it's important that the compatibility between Micrium and Datalight goes beyond just this interface that we have between our software modules. Datalight and Micrium really have a lot of similarities philosophically. We've historically both been organizations that write very reliable code. We're very focused on writing code that adheres to standards, code that can be used in safety-critical applications. So ultimately, what you see with Datalight and Micrium is this philosophical match, and it means the combination of Datalight and Micrium makes sense for a number of reasons. So in the next couple of slides, we'll consider in a little more detail why developers choose Datalight and Micrium for challenging embedded systems. And I'll start off here with Micrium. Oftentimes, when I give training or give presentations like this, I'm asked to distinguish Micrium's kernels, MicroCOS 2 and OS 3, from some of the competing solutions out there. And I think in many cases, developers who want to see that differentiation are looking for performance differences or features. But I think the differences that Micrium offers are bigger than that. I would really point to three key characteristics that distinguish Micrium from our competitors. And the first of these would be the quality of our code. So this is kind of going back to what I was discussing earlier, this philosophical match that we have with Datalight. Micrium has always been very focused on writing quality code. We've used coding standards from day one. And you can actually see that in our kernels, the MicroCOS 2 kernel, has a history of use in certified systems. These are systems where we have very demanding requirements. We've been used in certified aerospace systems, which uphold the DO 178B standard, certified medical systems, that's IEC 62304, and also IEC 61508 based industrial control systems. So certainly evidence that we put a lot of effort into ensuring that we have quality code. I also think what helps distinguish MICRIM from our competitors is what goes around the code. So that includes our documentation, first of all. A lot of developers learned about real-time kernels from some of MICRIM's books. The original MicroCOS book is very popular amongst embedded systems developers. And so the books are intended to introduce just general embedded systems concepts and to describe, of course, MICRIM's implementation of those concepts. And beyond the books, we have users' manuals, application notes, blog posts, a variety of other sources of documentation, so that as a developer, you can always be assured that there aren't going to be any mysteries in MICRIM's code. You'll know how everything works. The last distinguishing factor I point out for MICRIM is our technical support and our training. You get a year of support with every MICRIM module. So that's access to our support team, access to any updates that are released during that time. So that's certainly very helpful as you're going along in your project, overcoming whatever difficulties arise during that process. And then we also have training that can help you get up and running quickly with the software, introduce you to the software's APIs and basic concepts. And really between the training and the support, developers who choose MicroCOS 2 or MicroCOS 3 have all the backing needed to use the software successfully.
Really the key things that make these two options a compelling solution are the coding standards, the documentation, and the dedication to supporting our customers. Both Reliance Edge and the MicroCOS are scalable to meet our customers' needs. Our companies share a wide range of vertical markets, and our combined software provides scalable and certified solution for safety-critical applications.